All right. So now that we've dipped our toes into the world of aromatic reactions and we know how to add and remove and block and do all these things with aromatic systems, let's go back and talk more about carbonyls. When I first was introducing carbonyls for you guys, back when we, we actually, met face to face, way back in the day, right? Yeah, it's been a long year. But anyway, I mentioned to you that carbonyls are extremely useful functional groups, and there's just a lot of chemistry we can do with them. And so the first part of the carbonyls, we talked about how to make them, how to reduce them, how to oxidize them, in the kind of basic idea of carbonyls. And then, so for the next I don't know, maybe 2 or 3 or maybe even 4 lectures, we're going to talk about what we can do, some more chemistry that we can do with these carbonyls. Okay? But first, a little bit of a review. You guys should all know this. But if I take Mr. Ketone, okay? If I take Mr. Ketone and I put this under, you know what? Let's start with acidic conditions, okay? If I put this under acidic conditions, we can establish an equilibrium with the enol. Okay, right? We can do a tautomerization, right? So tautomerization. I always have to remember how to spell it. Tautomerization, right? And get to the enol form, which looks like this, right? Of course, there's this is an equilibrium, and it heavily favors, right, the keto form, the ketone form. Okay, just for simplicity's sake. So, we can do the same thing under basic conditions, right? So if we take our ketone under, let's put it with some hydroxide, we get the enol 8 form, though, right? The enol 8. Which usually reacts with water to get the enol, right? Now, why did I stop and tell you that and all this kind? Well, just I'm going to be throwing out the term enol 8 as we go through the semester, as we go through this series here, and so that's just what I'm talking about here. That's the enol 8, right? But in both cases, we end up at an enol, right? Okay. That looks like it's a funny looking word there all of a sudden, but maybe I just haven't had enough coffee this morning. Anyway, good practice. Pause here. Can you guys do the mechanisms to get from the ketone to the enol forms, right? So can you guys do the mechanisms without looking back at your notes, or can you guys figure it out? We'll start at the top here. We're under acidic conditions. Remember, when we're under acidic conditions, we typically always use those in the first step, right? And especially with carbonyls, remember that to get them to do something, we kind of got to convince them, right? So now that we have this, right? Let me just kind of draw this a little bit nicer here. All right, now that we have this, what's going to happen? I can't use red, otherwise it gets confusing. Let's do green then. Some water will come in and pluck off, right? That hydrogen that is right next door to the ketone. Okay. So this hydrogen here, right, the one in green, that's an alpha hydrogen, and we're going to be talking about those quite a bit. So just keep that in mind when I talk about a position that's alpha to a carbonyl, and it's right next door to it. Okay. So there's our acid-based mechanism. Our base mechanism is pretty much the same, right? Except with a base, we're going to use the base in the first step. You know what? Let's do this green just for emphasis sake here, right? There's our alpha hydrogen again. Okay. So after this first step, we've got this. That's green, right? That's green. And then you got some water around, right? So that looks nice. All right. Make some nice Christmas enols. Okie dokie. Okay. The point being, we can actually draw a couple resonance structures with our enols here. Okay. Let's do this in black, right? Oops, I left something off, so excuse me here for just a second. Something like this could happen. It's like I knew something looked weird. Okay. And that should be black. Alright, so all of a sudden, right, we can put a negative charge on that alpha carbon. Okay? And this isn't a big surprise, right? This is basically just a resonance structure of this right here, right? I'm just kind of going backwards. And we can do something similar here, right, where we could draw a resonance. With the acidic form here also, where we do this and this, right? And so we have a negative charge in both cases on that alpha carbon, and that's going to be important, okay? That's going to be important because we've got a negative charge on a carbon. Those are pretty darn reactive, right? So if we take any of those negative charges, right? Let's just drop this one here, okay? So if we take this negative charge here, and we put it in the presence of Mr. Electrophile, okay? It doesn't matter what Mr. Electrophile is, it's just something with a positive charge. Then you guys can see what's going to happen, right? And as soon as we put that negative charge in with a positive charge, then we're just going to end up bringing those two together. And what we end up doing is adding something to the alpha position next to a carbonyl. And that's really useful for us, right? We can start to make some, we'll start to make some halogen bonds. We'll learn how to make some carbon-carbon bonds. We'll learn how to clip two larger molecules together. But if we can generate this enol intermediate, or this enol-8 intermediate, okay, then we can start to add things to the alpha position, all right? If we have, just a little bit more terminology here, if we have a larger, right? Let's say we have a larger carbonyl group. We've got, this would be an alpha position, this would be an alpha position, right? This would be a beta position. This is our gamma position that's out here. I think that kind of looks like a Y, but you know, a little bit weird. It's a gamma. And then I believe delta is one further out. Honestly, I should have, I'm kind of thumbing through my notes here real quick. I forget. I think delta is one more out there. But we're never really going to, we're not really going to be doing anything with that. So, alpha, beta, and gamma positions. We're going to start by talking about alpha position substitutions, and then we're going to come back and we're going to learn a little bit about the what we can do at the gamma position there. But we're going to call those 1,4 versus 1,2 additions. And so, but either terminology there is going to be adequate for what we need. Okay? All right. So let's learn a thing. Okay? Let's learn a thing. Let's learn our first reaction here. And the first reaction we got to know is, well, how are we going to grab that hydrogen off of there? All right? Well, we can use something like hydroxide, and that would be fine. But our friend that we're going to kind of introduce here, and we talked about it a bit in class before, is something known as LDA. Okay? And LDA is our buddy lithium diisopropyl amide. Okay, lithium diisopropyl amide. So we got an amide, And we've got isopropyls around, and it's got a negative charge, and we've got a lithium that's kind of hanging around with it, okay? That's our buddy lithium diisopropyl amide. Lithium diisopropyl amide is an extremely powerful base. It's also a bulky base, so it's often kind of introduced when we talk about T-butoxide, because this is just another bulky base, but this is a much, much stronger base than, well, I got to be careful. Maybe not much, much stronger, but it's pretty significantly stronger than Whoops. Well, sorry, guys. I'm making some noises. I just kicked something under my desk. But anyway, it's a bulky base. It's used to deprotonate things, and it's very commonly used to deprotonate the alpha positions of carbonyls because we don't want our base to act as a nucleophile. Right, and if we use something like hydroxide or maybe even, ethoxide and things like that, we have to be careful because those things can be nucleophilic, right? But because LDA is such a sterically encumbered base, then we don't have to worry about acting as a nucleophile, right? It's just going to come in and deprotonate something, okay? So the point being that when we add LDA into this, right, we tend to form the enolate, right? And remember, this is an equilibrium, right? So, right, we have that all going on here, right? And then we can use that to react with we can use that to react with whatever electrophile that we have in there, okay? We could also use something like sodium hydride, and that would help like shift equilibrium in some cases, and you can read this online. There's a couple different bases that we can use here. I don't want to sit here and get bogged down in all the different bases that we can use, but there is LDA we're going to be using quite a bit, and so I just did want to introduce that, okay? So, let's do, let's see how much... Yeah, 12 minutes. Okay, yeah, we got time still. So let's do a quick reaction here, okay? If I take, let's say, let's take this guy here. All right, and I put in some sodium hydroxide, and I put in some bromine, okay, and I let this kind of react away, right? We've got a strong base, we've got a decent electrophile here, well, maybe not decent, but it's reasonable, I guess. Nice. Dot, dot, dot. Okay? So we'll end up putting halogen at the alpha position next to a ketone. And that's pretty darn useful, right? We can do a lot with a halogen. We can eliminate, we can substitute, we can, we'll learn how to clip things together using that, right? So there's a lot that we can do with the halogen, okay? But we've got a problem. Okay, the reaction doesn't stop there. In fact, it's really hard to stop this reaction. It goes all the way to the dibromo derivative. And you're like, well, geez, that's useless, right? Sort of. We'll actually learn something pretty useful here in just a minute. Okay, but let's look at the mechanism real quick, right? So, let's go through the mechanism, right? Let's get our strong base ready to go. Boom, 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 boom. Hydrogen, right? I'm just going to stop here because this is the resonance form that we use in the next step. Obviously, the enolate's in there, blah, 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 all that kind of stuff. I think you guys get it at this point, right? But this is going to be the reactive part. I've noticed in the recordings for the videos, it's pretty prevalent when you hear my pen clicking. I wish there was something I could do about that, but there isn't. So, anyway. Okay, so that's how we get to this here. And then as we add a halogen there, it actually makes that alpha position more acidic, right? Because since we're generating that negative charge and we've got an electronegative atom on there, right, we can stabilize it a little bit easier, right? All these kind of things, right? And so this reaction is just going to continue if we're under basic conditions, okay? To the point that, right, to the point that if we come in with this, so if we put in sodium hydroxide and we have a bunch of bromine around, okay, we are actually going to end up forming the carboxylate. Plus CHBr3, okay? And this is known as the haloform reaction. So what in the world is going on? So chloroform, this is bromoform here, right? We haven't really talked about this ever, right? Because nobody talks about it except for me in the book, right? So that's our buddy bromoform, but you know, in the lab we have used chloroform, which is CHCl3 before, right? Especially when we do NMRs, we use deuterated chloroform. There's iodoform, which would be CHI3 minus. Okay, let me try this all over again. Iodoform, since apparently I can't talk today, would be CHI3. There it is. Okay. So chloroform, bromoform, iodoform. I've never heard of fluoroform before, but I mean, that's probably a thing that somebody made at some point, so, but not really useful for us. Okay, who cares? You're rambling, right? Here's something useful, okay? So take a look, right? We start out with a carbon there, that's alpha, okay, to a ketone, and that carbon gets chewed away under relatively mild conditions, right? Under relatively mild conditions to form a carboxylic acid or a carboxylate, and we either precipitate out or we just form this bromoform or iodoform along the way. Okay? And actually, this is a reaction that we would do in the lab. This is what we would do is the iodoform test. And iodoform here, if we do this and we have alpha, if we have a ketone there that's got a methyl group at the end, like we have in this case, you would precipitate out iodoform, which is actually a yellowish solid that you would see form along the way. And so it's a qualitative test to see whether we have alpha hydrogens next to a ketone there, right? Whether we have a methyl ketone, okay? But we can get rid of a single carbon and turn it into a different functional group under relatively mild conditions. So actually it is kind of useful for us. But the problem is, like up here, we can't stop it, right? If we have a methyl group here, right, if we have a methyl group, it's going to completely go all the way to the bromoform, right? But if we just have a secondary carbon there or something, right, it's going to stop, but after we die substitute. Which, again, could be useful in some cases, right? But here are two reactions where we can put either a halogen next door to a ketone, or we can transform a methyl ketone, right, into a carboxylate there. The mechanism for all these are the same. It'd be good practice for you guys to see if you can figure out or draw through the mechanism how to get this one here. Okay, it's the same series as what we did right above there, right? We just eventually end up making a very good leaving group, right? We end up making a very good leaving group with our halogenated carbon there. Okay, good practice. If you guys can't get it, drop me an email, give me a call, whatever you need to do, right? But there it is. So how are we going to fix this? How are we going to get it so that we can stop at a single substitution? Well, we're going to have to change our conditions a little bit, okay? And we will, yep. So we're about 20 minutes here, right? So we will do that next time. We'll pick up how to do a single substitution out of alpha position with a halogen on a carbonyl group.